Okay, welcome back. So we're going to go through the scenario where we have a categorical explanatory variable, especially one that has more than two categories, and how they appear as indicator variables in our multiple linear regression scenario. So here, if you add a categorical variable to your model that has two or more categories, things to consider: how many terms it's going to add to the model. It's going to add however many categories you have minus 1. So if you add a variable that has 5 categories, it's going to add 4 variables to our model. Specifically, variables called indicator variables. So by default, R is going to make one of your categories the default, and then add a term for each of the other categories. That is why it's a minus 1. Often people might go ahead and use releveling. They might make the control treatment the default and have the different treatment levels be the added terms. We call them indicator variables or dummy variables. The idea is, one, if whatever condition, like condition or category, is present. And it'll be a 0 if not. So we're going to go through a just real quick example just to show what we mean here. So indicator variables, they only have 2 values, 1s and 0s. That's just indicate, is this particular category present? So this is a very old data set here. We went ahead, it's a student survey, and so we have social, so this is minutes spent on social media that students reported. Political party, so here we have it split into 3 categories: Democrat, Republican, no party, or other. So basically Democrat, Republican, and other pretty much lumped in there. And then phone, so this is minutes spent on phone daily. I would not argue that this is actually an excellent model that I fit, but I want to illustrate what we mean by fitting this model here. So here, I went ahead and said, I want to predict how many minutes students spend on social media based on what political party they are affiliated with and the number of minutes they spend on their phone daily. I'm not saying it's an excellent, meaningful use at all of a model here. I just wanted a quick example. So here, looking here, so intercept, this is always going to go with the y-intercept. Beta 1 or beta, like no party or other, see, it added 2 terms. I have 3 parties or 3 categories, so it added, it made Democrat the default because it became first alphabetically. Absolutely, you can change what the default is if you like. No party or other comes first. Republican comes third alphabetically. And then phone is the 4th thing in there. So if I wanted to go ahead, I wanted to set this up, intercept, I'm going to go ahead and look at these estimates. So my estimate, I'm just going to take out to 5 spots, 57.75. And it looks like this is a minus 1.53 times no party. So this is going to be a 1 if they're no party or other. And it's going to be a 0 if they're anything else. So if they're Republican or Democrat, that's going to be a 0. This will also be minus, so minus 16.57. I am only rounding to 2 spots here, times Republican. So this will be a 1 if the student identified as Republican, a 0 if they identify as anything else, plus, this is positive here, so 0.38 times phone. So what we put in there is just the number of minutes for phone use in a day. So moving forward, I'm going to go ahead and interpret this line will look different depending on which party they're in. So here, I threw it into here. So there are 3 different levels of political party. There's the Democrat, which is the default because it comes first alphabetically. There's no party or other, and Republican. So I'm going to go ahead and fill out, like, what does this regression line look like for each of the 3 categories. So here, what is the equation for a line that is Democrat? So I'm going to put social hat because I'm trying to predict the social time. So it'll be 57.75 minus 1.3. And then if they are Democrat, they are not no party or other, so I will plug in a 0. Minus 16.57 times, and if they are Democrat, Republican's going to be equal to 0 because they're not Republican, plus 0.38 times phone. So I can go ahead, I can simplify these terms that have zeros in them, just go away. So social hat is going to equal 57.75 plus 0.38 times phone. So this will be my least squares regression equation when I have a Democrat student. I can go ahead, I can go through all the others here. So social hat is equal to 57.75. So suppose the student I'm looking at now is no party or other. That means here I want to plug in a 1 because now that is true. So minus 1.53 times 1. So if I plug that 1 in there, this means they're not a Republican, so I'll plug in a 0 here, plus 0.38 times phone. So now I have like terms here. I can combine them. So I'll have social hat is equal to, go ahead, take 57.75 minus 1.53, get about what? 56.22. This goes away, plus 0.38 times phone. So there you are. And I can go ahead, I can repeat this if they are Republicans. So still going to be social with a hat. You always want to have your hat there. We're going to jump on it the second there isn't a hat, because the hat means we're predicting this using sample information. So minus 1.53 times, here, only put a 1 if they're no party. If they're Republican, this isn't true, so we'll put in a 0. Minus 16.57 times Republican. They are Republican, so we will plug in 1. Plus 0.38 times phone. You could also think of this as X4. As long as, if you use X4, you do need to have it labeled somewhere that it is equal to minutes spent on phone. Oops. So social hat, you can go ahead and simplify here. You have these 2 like terms. So 57.75 minus the 16.57, that's going to be 41.18 plus 0.38 times phone. So effectively what this categorical variable does in this scenario, it shifts where the y-intercept is. It looks like there's a shift down if in the line for if the student is a Republican versus if they're either of the other 2 parties, that kind of thing. So effectively what we have is we have the equation for 3 different lines, hence the multiple linear regression idea. We now have multiple lines that we would have plotted here. That's what it comes out to. So now that we've made it through that example, and I know that probably wasn't a very realistic one, we have another multiple linear regression example. So remember, multiple linear regression, it's going to be where you have a quantitative response variable and at least 2 explanatory variables. They can be any mix, they can be categorical, they can be quantitative, they can be both, that kind of thing. Well, I mean, not at once, but. So here, this scenario, we took this from fall. I'm not sure if it's great now, but we have 111 randomly selected hospitals in the US, which, I mean, they could be really spread out. They're used to assess factors related to the likelihood that a hospital's patients acquire an infection. So the variables we collected was infection risk. This is on a scale, I feel like it might be, I don't remember if it was 1 to 7. I forget exactly. It was a little funky. There wasn't a whole lot of information on it. There is the average length of patient stay. So like at this hospital, the average patient stay was however many days. The average patient age. So if you took that hospital, the average of the patient's ages. And then how many x-rays are given. I believe it might be longer than a day, but it's one set amount of time. So what we want to do is we want to determine is the average length that patients are staying at a hospital, the average patient age, and the number of x-rays that are being given. Do those, at least one of those, are they useful in predicting what the infection risk is going to be at a hospital? So one of the first things we're going to do, we're going to put together our scatter plot matrix. I find it useful to put my response variable on top because I want to look across and see, do I have relationships? Because when I do, so like here, I would say, yeah, it looks like stay and infection risk, they have a roughly, positive linear relationship. I have this set up in such a way that I have the correlation coefficient between the two here. So I would say, it's moderately strong, like a moderately strong linear relationship. It's not very strong. Here, it does not look excellent, but you can even look that's really, really close to 0. Here, it looks like there's a relationship. I don't know if it's super high, it's moderately weak, that kind of idea. So the idea is when you look at the relationship of the response variable with the explanatory variables, you want to see strong relationships. When you look at the relationships between the explanatory variables, like with each other, you do not want to see a strong relationship. If your explanatory variables are related to one another, it might be the equivalent of double dipping, that variable 1 explains pretty much what variable 2 does. However, the model can't tell who to give the credit to, and then you're going to get something really funny looking. So, I might be a little worried that it looks like there's a relationship, like in some places here. None of them are huge, but here you want relationships. Here you don't. You don't want there to be any sort of relationship between the explanatory variables. Often, when you do have a strong relationship between explanatory variables, what you're going to do is drop one of them because you don't want to double dip. So starting here, our first place that we're going to start is asking, is at least one of them useful? So is at least one of the explanatory variables, and I list them. So length of patient stay, average patient age, or number of x-rays, is at least one of those explanatory variables a useful predictor of infection risk. So here I have it labeled that length of patient stay, x1, average patient age, x2, number of x-rays, x3. So these are the order that I'm going to be putting them into my model. So when you are in R and you have mod and you fit LM and you have infection risk, I forget exactly what we called it, and then you'll have stay plus age plus x-ray. This is implying that this is the order that I put it into my model. So here I am interested in beta 1, so that's the slope coefficient associated with the length of patient stay. Beta 2 is the slope coefficient associated with average patient age. And beta 3, which is the slope coefficient associated with number of x-rays. So that these are the parameters of interest that I am interested in making a statement about. So from there, I'll go ahead, I'll list my significance level. Typically, we will give you one. If you don't, you can usually assume alpha is equal to 0.05. If one doesn't seem to be there and you want to double check, you are always, it's definitely okay to go ahead and send an email and ask us, hey, should I assume a significance level of this? I don't see it. Because we can either help point it out or we can agree, yes, use 0.05. So for the model utility F-test, we start out assuming nothing in this model is useful. So the slope related to patient stay, and the slope related to patient age, and the slope with x-rays, all of those are equal to 0. So none of the explanatory variables, this is obviously going to be not quite a full sentence here, variables are useful. Specifically, none of them are useful in predicting the infection risk at hospitals. So if statement 1 is saying none of them are useful, in order for this statement to not be true, only at least one does. So at least one. And I'm going to write beta I is not equal to 0. Now have I equal to 1, 2, 3. So it doesn't imply that all of them are useful. It just implies at least one. At least one of them is useful, which might kind of hint at the follow-up we'll have. If we ask, hey, is at least one useful? And you go, yes, our follow-up will be, okay, well, which ones? That kind of idea. That's our natural progression here. So looking at my conditions, I have a residuals versus fitted plot. So for all of the observations, all 111 hospitals, I calculated what the regression line would have predicted and took the difference between that and what was observed for infection risk. Looking here, this is roughly nice and even. I am actually very, very pleased here. This is really, it looks good. The normal QQ plot, these points all really roughly fit the line. This looks really good as well. So getting back to the actual questions, is the sample random and representative of the population? It is random. We're going to say yes, although I'm not sure how I feel about 111 randomly selected hospitals representing all the hospitals. There are definitely a lot of different types of hospitals out there. I mean, are you taking children's hospitals? Are you taking private, public? I mean, they're wildly different. So then here, do the residuals indicate the 4 conditions are met? So linearity, independence, normality, and constant variance. So for linearity and constant variance, these two, I'm going to look to the residuals versus fitted. This is where it's saying I have nice, even scatter. It looks good. I would say yes, that linearity and constant variance are roughly met. I don't see fanning out, funneling in. I don't see any curve shapes. It looks good. Normality, I would say this is met as well. Independence, that's going to require you knowing that, hey, as long as none of these hospitals are, related to one another, it's probably fine. So as long as like one's not, neighbors to the other, it's probably okay. So reasonably, it's probably okay to assume that these would be independent hospitals if they weren't, interdependent. So here we go ahead, we fit the model. So if we are doing the overall F-test, we are paying attention to information here. So our test statistic for the overall F-test, wait for it, is an F statistic, right? So it's going to be an F statistic equal to, and it's going to be right here. So 20.87, our numerator degrees of freedom were 3. One thing that's cool is, hey, look here, 3, right? That's where that comes from. Our denominator degrees of freedom are equal to, so my total sample size minus 4. So it should be 111 minus 4 is 107. That's why it's n minus k minus 1. It's including the intercept there, so 107, which you can see here as well, and there. It's written both places. in the p-value, it's going to be always a one-sided p-value with an f-test. The f distribution is very right skewed. It's always going to be one-sided. And looking here, it's really, really tiny. So I'm just going to say, hey, it's less than 0.001. That's pretty small. So looking here, f statistic is equal to 20.87. Numerator degrees of freedom was 3. Denominator degrees of freedom was 107. My p-value was small, so less than 0.001. Looking at the 0.05 significance level. So knowing all this, my p-value is tiny. It's tinier than the significance level, so I'm going to reject. So we reject the null hypothesis at the 0.05 significance level, and here's all the information there. Then I want to go ahead and use that spectrum from earlier, say, well, how strong is this evidence? If my p-value is that small, it's pretty strong. So you could say very strong, convincing would be okay as well. So very strong evidence that at least one of the variables, and here I list them, average stay, average patient age, or number of x-rays, is a good indicator of, or a good predictor of, and here's my response variable, so infection risk. So at least one of them is a good predictor of infection risk, which isn't too surprising. Whether or not all of them are useful, that's a whole other question, which is going to be our follow-up. So looking there, now that we've performed the model utility f-test and we found at least one of them is useful, we are going to go ahead and pursue, well, which ones are useful? So things to note here. We have our equation. We have y hat. We should have y hat is predicted infection risk. And then we have, since we used x1, x2, and x3, you do need to have them labeled. It is very, very important to keep track of this because it's extremely important to mix things up if you don't. So now we're going to perform the individual t-tests on each of the betas to see, well, which ones are useful. Specifically, if I add just this one, already including all the other explanatory variables, is it useful? So which are significant? So these t-tests, they're going to test, hey, is it useful to add this variable when including all the others already? So looking here, we never ever test for beta naught pretty much. It's really weird. It's odd to get rid of a y-intercept. It forces stuff through the origin and things get really goofy. We don't do it too often. It's odd. So we're interested in slope coefficients. We're interested in beta 1, beta 2, beta 3. So here, if I want to look at stay, I would go, okay, well, my t statistic is 5.488. So the degrees of freedom are the same as the denominator degrees of freedom. So that's your n, like your total sample size minus k plus 1. So minus 4. So 107. The p-value of, that's pretty small. So p-value less than 0.001. So knowing this, I would say, okay, well, average stay is a significant predictor. Oops, I'm trying to combine words. Significant predictor of infection risk. Then if I look at patient age, so now I'm looking at this row 3 here. So I'm going to look my t statistic. So my degrees of freedom are going to be the same for all 3 of these. That's one thing that's cool. So my t statistic will be negative 0.935, and that's not very far from 0. And sure enough, here we have this p-value. It's pretty big. It's equal to 0.3516. Oops, I'm writing on the wrong line. See, I was wondering why I had so much room. There we go. So considering this, I would say the average patient age is not a significant predictor of the infection risk when you include stay and x-ray in the model. So here I'm going to say not significant. So I mean, on its own it might be, but when you're already including stay and x-ray, it doesn't add a lot more information about what's going on with infection risk. That's what we're getting at. And last but not least here, we're looking at number of x-rays. So this is the last row, row 4. I have a t-statistic of 3.315. Degrees of freedom are still 107. My p-value, it's fairly small. It's equal to 0.00222. So knowing this at the 0.05 significance level, so that is an important note that that is what I was using as a cutoff. I would say that number of x-rays is significant. So typically what we do here is if we find that we have one or more variables that are not significant, backward selection says drop the one that has the biggest p-value. Only ever drop one at a time. Never drop more than one at a time. It can be a total disaster. So here I have age, and this is going to be something that is this p-value is very large. I'm going to try fitting this entire model again, excluding age, and see how that goes. That would be our normal thing. If all of them are significant, leave it. You're done. You're good. But if you have multiple, like one or more specifically slope coefficients that are not significant, then you're going to go ahead and work backwards. Remove only one at a time. Although, if it comes down to a categorical variable, you can't remove just one level of it. So if any of the levels are useful, you're probably going to end up leaving it. So here, I've refit, and just to look, the residuals, they still look good. They haven't really gotten really gross. So my overall utility F test looks like, now my F statistic maybe is a little bit higher, I think. Oops. My F statistic is 30.9 on 2 numerator degrees of freedom and 108 denominator degrees of freedom. Because notice, 111 minus 3 is 108, so that changed. P-value is very, very, very tiny, so 0.001 less than. So we're definitely going to reject. Like, we reject the null. At least one of these is very useful. So with a p-value that small, there is very strong or convincing evidence that at least one of the variables, average stay or number of days, or sorry, number of x-rays, is a good predictor of infection risk at U.S. hospitals. So specifically, I mean, if we looked at these individual rows, we'd probably be pretty happy because now we look like we're in a place where all the variables do have a small p-value, which we might get to, yeah. Okay, as promised, now that we've decided at least one of the variables, average stay or number of x-rays, is useful in predicting the mean risk at a hospital, now we're going to go ahead and figure out, okay, well, which ones are useful? So looking at the first, because we pretty much, I'm not saying that we never apply this, but we generally won't test the y-intercept there. So the first one right here, so when including the number of x-rays in the model, average stay, so I'm focusing on average stay, is or is not a useful predictor with a mean infection risk with a t-statistic of, I have 5.412. My degrees of freedom are the denominator degrees of freedom here, so from the F test, so 108. And the p-value, that's really little, so less than 0.001. So if I have a very small p-value, what I'm going to say here is, no, stay is useful. So even though I already have x-rays in the model, including the average stay at a hospital, is useful. It gives me more information about what's going on with the average infection risk at a hospital. So then my second one, I'm going to look here. So I'm going to fill in my information here. I have a T statistic of 3.246. My degrees of freedom are still 108. My p-value, it's pretty small, 0.00156. So because my p-value is pretty small, what we're going to conclude is, hey, when I include stay in the model already, adding the number of x-rays into the model is useful. So when already including the average stay in the model, the number of x-rays is a useful or significant predictor for mean infection risk. There's our support, our t-statistic, degrees of freedom, and our p-value. So summarizing our model here, now that we've reached this place where we said, hey, this is our final model, if you look here, both slope coefficients have very, very strong evidence to include them. So I'm going to go ahead and I'm going to write out my final model here. So 0.016, I'm going to go up to 3 places here. So here, it's very important to pay attention to what your labels are. So y hat is the estimated infection risk, x1 is the average stay, so I need to look here. So 0.404, if I'm rounding that way, times the stay, plus positive 0.019, if I'm rounding out to 3 places, right there and there. So I'm just working my way down here. And it is incredibly important to have your labels. So this is going to be the equation for my final model here, where all the explanatory variables are significant predictors of the response, which is infection risk. So interpreting. So now that we have this, we might want to interpret, hey, what does that slope intercept for stay mean? Or what would that slope intercept for x-ray imply? So slope for stay, so I'm going to focus here. So if I'm looking at stay, I want to hold the other coefficient constant. So number of x-rays constant. So when I'm looking at hospitals that have the same number of x-rays, and the only thing that differs between them is the average stay between the two hospitals. That's the idea. For every one, I don't know if it's 1 day, increase in average stay, average patient stay, the infection risk, because that's what we think will change here. So the infection risk is expected to, and here you need to look at the sign. So it's positive, so we'd say increase by 0.404 on average. So while holding the number of x-rays constant, if you have one hospital that has, the average stay is 4 days and another hospital, the average stay is 5, we're thinking the hospital with the 1 extra day is going to have a higher infection risk of about 0.404 on average. I can do the same thing for the slope of x-ray. So if I'm looking at x-rays, I need to hold stay constant. So while holding average patient stay at a hospital constant for every, so what is a 1 unit increase in x-rays? So for every additional x-ray, this is probably in a very specific span of time. X-ray performed, sometimes the verbs don't come to me. The infection risk is what we think will change. So the infection risk Once again, this infection risk, it's on the scale that I'm not very familiar with. I tried to find more information, but there was not a lot of info out there for me. So looking here, it looks like it's positive, so we think it will increase. So hospitals with, more x-rays have higher infection risks. That might be because depending on like certain types of injuries and ailments and whatnot are more likely to need x-rays. Those are maybe more vulnerable to infection risks. I mean, it's quite likely by 0.019. So when we have two hospitals that have the same average patient stay, but one of them has one more x-ray than the other in this span of time, the infection risk for the one that has one more, we think it's going to be higher by about 0.019 on average. So yeah, it can get a little clunky. I definitely find it useful to make sure that you say while holding and then list the other variables first. It is so easy to forget. We didn't include this in the simple linear regression part because there was only one. But if you have multiple linear regression, you have to account for the other variables. So once again, we can absolutely do confidence intervals here. So suppose I want to do a confidence interval for the slope for x-rays. So remember this 0, 1, 2. I am going to need information from here. So looking here, my degrees of freedom are 108. My B2, so that's my estimate here for beta 2. I'm going to use 0.0185. Just go out to the 4 places here. My standard error here, that's what goes here. 0.0057. And then this part, you can use a t-table or you can use R. R is really handy because it'll give you an exact t-star. I'm going to show you what I mean by that. So here we want a 90% confidence interval from that last slide. Our degrees of freedom are 108. So the percent confidence we have tells us which column to use. So percent confidence, 90%. Degrees of freedom, 108. So I'm going to look in these rows. Well, there isn't a row that corresponds to 108. There's one that corresponds to 100 and one that corresponds to 1000. When it comes to degrees of freedom, we tend to round down here. I would say, yes, I have a sample of at least 100, but I don't have a sample of at least 1000, so I don't like to round up. So if I line this up, my t-star is going to be about 1.660, which if you go ahead, you throw it into R, where you can get a more exact t-star critical value. So 0.95 is your quantile for a 90% confidence interval, 108 degrees of freedom exactly, so not 100. You're going to get t-star equal to 1.659. These two are really close. We would calculate it both ways. We wouldn't, put it down if you used either one. So I'm going to go ahead, I'm going to use the 1.659. So here, I now have my t-star. I have everything I need to go ahead and plug in. So my estimate here, so 0.0185 plus or minus that t-star that we just calculated, so 1.659 times that standard error, 0.0057. And then I'm going to get, definitely not mental math, I'm going to pause here so I can figure. Okay, so from there, just plugging in, get something like 0.0090 to 0.0280, if I'm rounding here. So remember, we were doing this confidence interval for beta 2, the slope associated with the number of x-rays, when we hold the average patient stay constant. So while holding, average patient stay constant. the 90% confidence interval estimates, plugging this in here, so estimates that for every, whatever 1 unit increase, so every one additional, or just one of those additional X-ray in that period of time, so of time, the response variable, so the infection risk, is expected to, and now this is where we need to look at our signs. So I have a positive value to a positive value, so both ends of this confidence interval indicate that we think that it's going to show an increase in infection risk. So increase by 0.009 to, I'm going to also write increase here. It's less important to write increase to increase both times, but when you have decrease and increase, it's absolutely important to include that. It's a little bit easier to write up when the signs are the same. So we think that infection risk on average is going to increase somewhere from 0.009 to 0.028 on average, with a point estimate of a 0.0185 increase. So it doesn't look like, honestly, I mean, I don't know the scale a lot, but it doesn't look like it necessarily increases by a lot. But chances are people a lot of times don't get one individual x-ray at once. They kind of get them in batches. So that's just something to consider. So while holding average patient stay constant, the 90% confidence interval estimates for every additional x-ray in whatever period of time this is in. The infection risk is expected to increase by 0.009 to 0.028 with a point estimate of a increase of 0.0185 in infection risk. So you can absolutely use this model to make predictions. So suppose I want to estimate the infection risk of a hospital that has an average stay of 1 week, so that's 7 days. And we're recalling that the average stay is in days, and performed 42 x-rays in a given time period. So looking here, so I am going to go ahead and just plug in. So y hat is my estimated or predicted infection risk, 0.06, so it looks like we did round a little bit here, or 0.16, plus 0.404 times x1 is average stay. We said an average stay of 7 days, plus 0.019 times, so I run it over, number of x-rays, so 42. So now we're just going to go ahead, it's algebra now, do this multiplication and this multiplication, and then add. Do not add first, it will go sideways. So just showing the next step there. In general, this setup was something we'll want, and then the answer, so 2.61. And this is a funky scale. I can't remember exactly what the deal was here. I think it was like a scale from 1 to 7. It was an odd number. So there aren't units to include here. If the response variable had units, this is where we would include them. So we estimate that, on average, for a hospital that has an average stay of 7 days and gives 42 x-rays in a given time period, they have a risk factor of 2.61. So here, estimate a little bit differently. That's because here we honestly didn't do nearly so much rounding. So I have a 95% prediction interval and a 95% confidence interval. And we performed it for the scenario where there's a 7-day average stay and 42 x-rays in a given time period. But we didn't label them, which is which. So I kind of joke with y'all, we really love doing this. So interval 1, interval 2. So for me, sometimes it's easier to picture them on a timeline. So, there's 0, 1, 2, 3, 4, and so on. So interval 2 goes somewhere like this. So that's interval 2. Interval 1 goes from a little over 2 to a little over 3. So remember, we know that the confidence interval, because it's for an average, it's going to vary a lot less than that prediction interval. The prediction interval will be wider. So the wider one will be my prediction interval. And remember, that's for one individual hospital. My confidence interval is saying, hey, for all hospitals that have an average stay of 7 and 42 x-rays, what do we think the average is? So interval 1, so with 95% confidence, the confidence interval, I know it's weird that we write confidence in both, but we generally will. So with the confidence interval estimates the average infection, because this confidence interval looks at the average of all. So all U.S. hospitals, because that's where we sampled from supposedly. So the infection risk of all U.S. hospitals that have an average stay of 7 days and perform 42 x-rays in that given time period has an infection risk, average infection risk between 2.09 and 3.09 with a point estimate of 2.59. So then it's fairly similar. So with 95% confidence, I know it's weird to still write that, but this technically would be true. So the prediction interval estimates that. And we don't write anything in here. The infection risk, because we're talking about the infection risk of just one. So we're not talking about the average of all, the infection risk of a single U.S. hospital. It could be like a brand new U.S. hospital. I mean, not literally brand new, but new to the data set. With an average stay of 7 days that performed 42 x-rays in a given time period is between 0.412 and 4.769 with a point estimate of 2.59. So here, our point estimates are going to be the same with this particular scale, because you cannot go lower than 0 with this scale. If either of these intervals went below 0, we'd cut them off at 0. But note that even if we did that, their point estimates will still be the same. They will always be the same there. Okay, so I believe, this was one more fun one. So here, these are just summary statistics for stay and x-ray in our sample. So there's 111 in our sample. I went ahead, I made a histogram of the average stays. So it looks like I had average stays from anywhere from 6.7 to 13.95. That was all I observed. I didn't see anything lower than 6.7 days. I didn't see anything higher than 13.95 days. When looking at x-rays, it looks like I saw anywhere from 39.6, and this is an average, x-rays in that given time period to 133.5 x-rays in that time period. So here, would we want to use our model to predict the infection risk of a hospital with an average stay of 10 days and 20 x-rays? What we want to do is we want to make sure we're not extrapolating. So here, 10 days, 10 is between 6.7 and 13.95. So stay is okay. But then if I look at number of x-rays, 20. So I want to know, is it between 39.6 and 133.5? No, it's lower. So I do not want to use this model to make a prediction for a hospital that has an average stay of 10 days and 20 x-rays, because I didn't see anything with that few x-rays. It probably would not be wise to try to use my model to estimate something that we just didn't see anything in that area. So no, because 20 x-rays is lower than what we observed than any of our observations in sample. This might become really, really relevant for one of those last couple of problems on an assignment this coming week. So just throwing that out there. And I believe, yes, so that is really just the tip of the iceberg. We kind of got into playing with linear relationships. Absolutely, you can do curve relationships. You can do exponential. You could do parabolic. I mean, there are so many different things. This is the tip of the iceberg, what we cover here in 314. There is so much more. There are transformations. There's logistic regression, so that's the scenario where you're looking at a categorical response. Much more complicated. Interactions, when you actually have your explanatory variables are being related to each other, like what happens there, multicollinearity. Don't worry, that we're not going into that. We just want you to know that every time we run into an instance where we said, hey, we don't meet these conditions, we have some sort of backup that we can use that has been well developed and whatnot. So know that there's more out there. So this has been fun. I hope you've enjoyed regression. And so for next week, and I'll hopefully get up soon, is we're going to be looking at quality control plots. So now it's your turn. Give it a go, and I hope I hear from y'all on the discussion boards.